Welcome. In this lecture, we're going to be talking about motion in one dimension. This is coming from chapter 2 of the textbook. We'll be talking about position. Oh, no, we won't. We talked about that already. We will be talking about one-dimensional motion and kinematics equations, and then we're going to do a couple of examples. One-dimensional motion. So let's say there's no motion. And the position is given by this equation, x of t equals a, where a is the position of the particle. So we have two graphs here. We have our position graph, which is the position with respect to time. And then we have our velocity graph, velocity with respect to time. So in our position graph, we see that the position is, our value here is marked at A, and then it's just a straight line telling us that our object is not moving. And since in the previous lecture, we talked about how velocity is the time derivative of position, if position isn't changing at all or with time, the velocity is 0 the whole time. Okay, now we have motion with a constant velocity. It's given by, the position is given by this equation, x of t equals a plus b times t. And a and b are just scalars. So a is giving us our initial position here, where x starts out, or where our position starts out when time equals 0. So that's what A is, because also if you just look at the equation, if you plug in 0 for time, it just gives you A. So that's where it starts. And then we have this positive slope, and the slope of this line is B. Yeah, sorry. And the slope of this line, because again, velocity is the time derivative of position, the slope of the line is velocity. So now our velocity graph actually looks like the position graph on the previous page, where it's just a straight line and a specific value. That's telling us that the velocity isn't changing, it's constant, but the position is changing with time, because there is now a velocity. So another thing to think about, so the 0 line is here for position. And so we start at position A, which isn't 0. And then we slowly increase in distance as in we get farther away from the origin. So one thing I want you to think about when a position is positive or negative, it just means that there's some set origin and it is either moving toward or away from that origin. So that's an important thing to keep in mind. Now, if we have accelerated motion, so now we have two examples with this one. We have this equation for the position, which is a plus b times t plus c times t squared. And then we also have x of t equals d cosine omega t. So this first equation up here is shown by this position graph, where it starts at A, because remember we covered that part. And then initially, the slope of the line, which is tangent to a curve, is what the slope is equal to B, but then over time, the slope gets bigger than B. So initially, the position is 0. The velocity starts out not at 0, like not when time is 0, but when, like around 1 second, velocity starts out as v and then gets bigger than v. And then this other example with the cosine being the equation for the position, this gives a cosine graph where the position oscillates with respect to time, and the slope kind of changes along with that. You might see this with, like, if you attached a mass to a spring and it would go like up and down. I mean, I don't know that that position is cosine wave, but it's the same idea of oscillating. Now we can look at an example of changes in motion. So specifically, we have a car accelerating and braking. This time the acceleration graph is at the top here, right? Yes. Acceleration, velocity, and position. So let's start down here with the position graph. It starts at rest, so there's no motion. And then we have this period where it's accelerating, and we have we don't have a linear position graph, which makes sense because the velocity is accelerating. So the velocity graph is going to be linear, and the position graph is going to kind of have this little subtle curve to it. It's a little hard to tell. And then we have this phase where it's moving at a constant velocity. So this is where it has a constant slope. And then braking, so that's decelerating. It's just negative acceleration. So we start with whatever velocity we had and then kind of slow down our motion over time. And then we're resting again. Now, let's look at this for the velocity graph. During the resting phase, there's no motion, there's no velocity. And then during the acceleration phase, we have this positive slope, increasing velocity. And then we have a constant velocity for a while. And then in our decelerating, braking, or decreasing velocity phase, in this chunk here, and finally we stop moving again, and so the motion is zero, or the velocity, and the velocity is zero. And then the acceleration graph, and remember, acceleration is the time derivative of velocity. So velocity is zero, acceleration is zero in this first chunk. And then when the velocity is increasing, it's increasing with a constant slope, which means acceleration is a constant value. Here, the velocity is constant, as in not changing. So there is no slope, or the slope is zero. And then we have a decreasing velocity. And in this time, that means a negative slope, and so a constant negative slope. So the acceleration is going to be flat but negative, and then we end up back at zero. Some things I wanted to point out. First, to note that when like looking at this position graph, we have a time where we're resting here and a time where we're resting here. But the position is not the same in those. The position is, when it's flat, it just means it's constant, as in not moving. It doesn't mean it only works at the origin. Another thing I wanted to point out is you can tell from looking at these graphs, or these parts of the graph, which part of the slope is larger. So thinking not of the whether one's positive or negative, if we just think about the magnitude, you can see that this takes longer to get from zero to this constant value. And this one, just based on how wide the chunk of time is along the x-axis, which again is time in these graphs, it takes less time to go from this constant velocity down to zero velocity. So that tells us that if they're going between the same velocities, but this one doesn't take as long, it must be accelerating faster or decelerating faster than this one. So that's one way to kind of recognize what's going on with the motion. Two is like you want to look at kind of where things start out, and depending on the situation where a value crosses 0, which isn't really relevant in this example. And then also how steep the slope is. Like if you know that the motion has 2 different phases of acceleration, you can tell if the graph is right based on if the steeper phase is first or second, for example. And then a brief look at these graphs for a falling object. Starting at the bottom again with position. So this time we're in Y. So normally in physics, X is going to be horizontal, Y is going to be vertical. And when we're talking about falling, we generally think of that as vertical motion. So we start at this height and then it falls in this parabola shape, which has a constant negative slope. So velocity starts at rest and then increases negatively. And that's a constant slope, so there's a constant value for the acceleration, and it's negative because it's a negative slope. And maybe just like a little extra info on this one. Generally, when an object is falling, like you dropped a ball or something, this slope is going to be the free fall acceleration or the acceleration due to gravity. We'll deal more with that later in the quarter, maybe next week. Okay, now I'm going to briefly derive some of the kinematics equations for constant acceleration. Okay, so let's start with velocity with constant acceleration. And we'll start out just with the equation for average acceleration. So acceleration is the change in velocity over the change in time. And we can expand out the equation for, or the numerator here. So we remember that the change in velocity is the final minus the initial velocity all over the time interval. And then this just gonna move these down. So we have a of x, or ax equals the final velocity minus the initial velocity over the time interval. And then let's say we're going to solve for the final velocity. So we will just, messed up, there we go. We will just multiply both sides by the time interval, and then we will add the initial velocity to both sides also. So that's going to give us, let's see, a x times delta t plus v x initial equals vx final. I'm going to write it in our more traditional order so that the start of the function is on the left side. There we go. So vx final equals vx initial plus acceleration in the x direction times the time interval. So that's one of the equations. Then we have position with constant acceleration. Sorry, I have to write the whole thing out. So I'm just gonna draw a little example graph poorly. There we go. And look like that. And I'm gonna indicate a couple spots. So let's say this is the initial time. And we'll say this is our final time. This will be our time interval. And then our initial, actually, it would be easier if my imaginary plot fell, no, more evenly. Pretend it falls on the corners there because that's not okay. And then the initial velocity and the final velocity. So this is a velocity versus time graph. So one thing to know, velocity is, well, I'll just write it. Velocity is the time derivative of the displacement or position with respect to time, or that's what a time derivative is. But how that also works is if you want to know what the displacement is, you can just take the area under the curve. So we have kind of two shapes here. So we have this, that's too far. This triangle, yeah, here, and this rectangle. So these are our two areas, and the height of the triangle is the displace or the change in velocity here. See, because it's the final and the initial. And we just saw that that's actually AX times the time interval. And then this here is just the initial velocity. And this is the time interval. So we can look at the area for each of these, because again, I said it's the area under the curve. So the rectangle, that's just the sides times each other. So the area is Vx initial times the time interval, and then the triangle, that's 1/2 base times height. 1/2. The base is delta t, and the height is this. So ax delta t. We can expand that out as 1/2 ax delta t squared. This is also equal to, you can also treat this as the change in velocity too. So you can do the same thing and bring in the acceleration a different way. So the displacement then comes from the area under the curve. Displacement area under the curve. And again, this is just, it's calculus. It's just, in one direction, we're taking the derivative. In the other direction, it's technically the integral, but we're not doing integrals right now. We are just taking the area. Much less scary. I mean, integrals aren't that. So the displacement equals these two things added together, because that is the total area under the curve. So dx initial delta t plus 1/2 acceleration next delta t squared. We also write this equation as x final equals x initial plus v initial x delta t plus 1/2 ax delta t squared. So for that, I just expanded out that this is x final minus x initial, so I just added x initial to both sides. I need more room. It's one more equation. So now a connection between velocity and displacement. So this time we can again start from the same equation as we did at the very beginning there, where we have the acceleration in x, then the change in velocity. But we're going to rearrange this we're going to multiply both sides by the time interval and divide both sides by the acceleration. And we're going to expand out the velocity. So that seems like a lot at once. It's not actually that much. Bx final minus Bx initial over the acceleration. Now we're going to bring back our equation that we just had on the previous page. So I'll write it as the displacement in x equals dx initial delta t plus 1/2 ax delta t squared. Now, I'm not going to do all of the algebra or any of the algebra for this next part. I'm just going to say that you plug in that equation there for the time interval into both of these for the time interval. And what you end up with once you do a little rearranging is Vx squared or Vx final squared equals Vx initial squared plus 2ax delta x. So that is the third equation. Okay, so here are these equations. And just note, like I derived these all in x, but they can be in any direction. They could be x, y, or z, but the thing you need to keep in mind is that you can't mix the terms. You can't have velocity in x, velocity in y, and acceleration in z. They do not go together. They are direction specific. So you have to keep that in mind. Yeah, so we have, just to review the equations, we have the final velocity equals the initial velocity plus the acceleration times the time interval. Then we have what I call the long kinematics equation because it is long. The final position equals the initial position plus the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. And then the last equation is the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. So now we're going to use these with 2 examples. Okay, so for this first example, I'll just read it. You drive your car at 15 meters per second, you hit the brakes and stop in 1.5 seconds. How far do you travel as you stop? So I'm going to teach you a strategy for solving kinematics equations. We start by writing what we know. So physics problems are mainly word problems, but I don't want you to be intimidated by word problems. You just need to pick out the important bit. So first important bit, you are driving your car at 15 meters per second. So the initial velocity is 15 meters per second. You hit the brakes and stop in 1.5 seconds. So that one is actually telling us 2 things, is that you stopped, so your final velocity is 0 meters per second, and the time interval of that stopping is 1.5 seconds. And the question asks, how far do you travel as you stop? I'm gonna define one more known just for right now. And that is, I am going to say that when we hit the brakes, because that is when time is 0, I'm also going to say that the initial position is 0 there. Okay. Then we write down our unknowns. And there's 2 main things we don't know. Obviously, one of them is the displacement, because that's what was asked for. And then we also don't know the acceleration. And I know there's acceleration happening here because I'm going from one velocity to another in a time interval. So now I'm going to write off the equations and I guess show you another kind of methodology thing. So I'm going to drop the x subscripts here because I'm just looking in x right now. So final velocity equals initial velocity plus the acceleration times the time interval. And then we have our long kinematics equation where the final position equals the initial position plus the initial velocity times the time interval plus 1/2 the acceleration times the time interval squared. And finally, we have the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. So now especially when you're getting used to doing these kind of problems, what I think you want to do is go through these. So these are your main equations. I want you to look at them and figure out what we know and what we don't know. So we know the final and initial velocity, and we know the time interval, and we don't know the acceleration. We don't know the final position. I said that the initial position is 0, so we know that. We know this, we don't know acceleration still, and we know the time interval. And again, we know these, and we don't know either of those. So once you do that, you see that, like, to pick which equation to use, you want the one that only has one thing you don't know, because that's how you can solve. So yeah, acceleration is not what we're asked for, but it looks like in order to find displacement, we're going to need acceleration, because both of the other two equations have two unknowns, and one of those is what we want, and the other one is acceleration. So let's find acceleration so that we can find the displacement. So we're going to take this equation, V final equals V initial plus A delta T, and we're going to solve for A. So let's see, that is going to look like subtracting the initial velocity from both sides, and then also dividing the time interval on both sides. So we end up with V final minus V initial over delta T equals the acceleration. And so our final, and then I'm going to plug in the numbers now. So the final velocity is 0 meters per second, and the initial is 15 meters per second. Time interval is 1.5 seconds, and this gives us negative 10 meters per second squared for our acceleration. Now we can choose one of these equations. You can use either or both of them. I'm going to use the long kinemax equation because it's already solving for what we want. We want x final, and it's already there. So x final equals x initial plus v initial delta t plus 1/2 a delta t squared. And then one of my favorite things is when something's 0, you just get to cross it out and not worry about it. And now I think we'll just plug in our numbers again. 15 meters per second for the initial velocity, 1.5 seconds, plus 1/2 negative 10 meters per second squared, with, excuse me, the acceleration, and 1.5 seconds whole thing squared. So this gives us a final position of 11.25 meters. So that is the, oh, I didn't put the unit. Units are important. So that is our final position. So just really quickly gonna go through what we did, because we have another example to do, and this lecture is getting a little longer than I want. So we wrote down our knowns and unknowns. We looked through the equations and figured out what equation only had one thing we didn't know. We solved for that thing we didn't know so that we could solve for the thing it asked for, which was the displacement. Now we're going to do this example from chapter 2, exercise 57. A ball is thrown straight up, a ball thrown straight up takes 2.25 seconds to reach a height of 36.8 meters. A, what was the initial speed? B, what is the speed at this height of 36.8 meters? And C, how much higher will the ball go? Okay, so this one is bigger, I guess, of a problem than the last one. I mean, for one thing, there's 3 parts, but also just a lot going on here. So let's start with our knowns. Let's see. Ball thrown straight up takes time interval of 2.25 seconds to reach a height, which is y position. I'm going to give it y1. For now, 36.8 meters. And we have these things that we're looking for, but there's two more knowns that we can mention here. So one of those is that the initial position we can take to be 0. So initial position equals 0. And then the other thing is something I mentioned, and actually I guess forgot that it was in this example, that acceleration when you're moving in the y direction, just like in normal Earth gravity, is the free fall acceleration, or g, which is 9.8 meters per second squared. And I'm putting negative here because, again, it's down, pointing down, and our motion is going up. So I'm going to quickly just draw our scenario because we're asked about like multiple things. And it's good to look at kind of the whole picture. So here is where it starts from the ground. So y initial is 0, and then we don't know what v initial is. And then we get to a certain point. This is when we'll call this time interval 1. This is time interval 1, 2.25 seconds. And actually, sorry, I'm not leaving myself enough room. And also at that time, y1 equals 36.8 meters. We don't know what v1 is. Okay. And finally, we have some maximum height, some y final that we don't know what it is. We don't know what this time interval is. And I'm going to tell you something important to know is in this sort of vertical motion, because the acceleration is pointing down the whole time, when you throw something up, eventually it's going to get to a point where the velocity is 0 because there's acceleration acting against it the whole time, and that is the maximum height when that velocity is 0. So we know what this velocity is. And then this whole time, acceleration equals negative g. And now, sorry, I didn't do my unknowns. So I will come back to those. I just wanted to draw the picture because I know it can be overwhelming. So we don't know the initial velocity. We don't know velocity at height y1. And we don't know y final. And we also don't know the time interval too. So from 1 to 2. So for part A, it asks, what was the initial speed? So that's where we're going to start. So let's look at our equation. V final equals V initial plus A delta T. X, we're going to go Y, not X, because we're in the Y direction. Y final equals Y initial plus V initial delta T plus 1/2 A delta T squared. And finally, V final squared equals V initial squared plus 2A delta Y. Okay. So for this first part, we're looking for V naught. And yeah, so let's take a look. Pick a color. There we go. So we know the Y final and Y initial. We know the initial velocity and the time interval. Oh, we don't know the initial velocity. Sorry, that's what we want. It's like I know too many things in this. We know the acceleration and the time interval. Okay, so it seems like this equation, but yes, I did skip the first equation. Because we don't know either of the velocities in this situation. We don't know initial or final because we're trying to find initial and we're not given final. And so that also makes this last equation not helpful because again, two unknowns. Okay, so let's use the long kinematics equation. So y final equals y initial plus v initial delta t plus 1/2 a delta t squared. So I'll do my favorite part, which is y initial equals 0. Also, apologies for going between y naught and y initial. Really hard habit to break. They are the same thing. Let's see. So that is 0. Then, so we're solving for v initial. So we're going to subtract 1/2 a delta t squared from both sides. A delta t squared. And then we're also going to divide delta t from both sides. Yeah. So we end up with v initial equals y final minus 1/2 a delta t squared over delta t. Yeah. And then we can just plug in numbers. So the y position is 36.8 meters minus 1/2 negative 9.8 meters per second squared. The time interval 2.25 seconds. Oops, not 22.5. 2.25 seconds squared divided by 2.25 seconds. So this is a initial velocity of 27.4 meters per second. Okay, so that was our initial velocity. So now we know it, 27.4 meters per second. Next, it asks what the speed is at that y1 position. Well, now we have the initial velocity and we can treat that as final velocity and use one of the other equations. And so now we do know the initial. So, but yeah, so we could use either one. I'm just going to use the one without the squares because it's don't need to make ourselves do more work. Let's see. I'm going to try and fit this on this page over here. Okay, so v final equals v initial plus a delta t. I'm going to quickly rewrite these with our subscripts. So v1 is the one we're looking for, plus a delta t1. Okay, so v initial 27.4 meters per second plus negative 9.8 meters per second squared times 2.25 seconds. And this gives us a velocity at position 1 of 5.33 meters per second. This makes sense because, as I said, the velocity here during this motion is pointing up, but the acceleration is pointing down, so we're decelerating. So we're slowing down. Which makes sense, or which we see here with our initial velocity being 27-ish meters per second and our final velocity being 5.3 meters per second. And then finally, it asks how much higher the ball will go. So now we look at these two, and this becomes our initial and final. And we will just look at the equations really quickly again. Apologies for all of the markings on them that are already there. Let's see, we know the velocities. We don't know the time interval. We know the acceleration. We don't know the final y position. We know the initial. We know the initial velocity. Oh, we don't know the time interval. We know the acceleration, don't know time interval. It looks like we're going to be using this equation. Because again, we know both velocities, we know the acceleration, and we want the time interval. So that's the equation we're going to use, and we're going to do it on the next page. So we have V final squared equals V initial squared plus 2A delta Y, or the displacement. So, let's solve for delta Y. So we are going to subtract V initial on both sides, or V initial squared on both sides. And then we divide both sides by 2A, and that will give us the displacement. And before we plug stuff in, we can see that this one's 0, because as I told you, eventually the velocity goes to 0, and that is the highest point. So the initial velocity here is that V1 we were using, so 5.33 meters per second, whole thing squared, and divided by 2 times negative 9.8 meters per second squared. The seconds are squared. And this is a displacement of 1.5 meters. So that is how much higher it goes. That is not the height here. It is not the value of height here, but instead the difference in height between these two, which is not to scale in my diagram. Okay. So I know this was a long one, but let's just quickly go through the last of it, or go over what we did. We wrote out our knowns and unknowns. We drew the situation to make it easier on ourselves, because it was kind of asking about technically 3 separate chunks of time. We looked at our equations in each of those scenarios. That's what all the colors are, to see which equation would work best based on what knowns and unknowns we have. And that is what we used to solve for the initial velocity. We went back and did the same thing to find the velocity at position 1, which we ended up picking a different equation for. And then finally, we were asked for the displacement from position 1 to the final position. And we got picked a different equation for that one, and got 1.5 meters. So apologies that this was so long. I tried to make this shorter, but I just filled the time. But I think it's really important for you to see these examples and me to talk through it with you. Especially if you're gonna do it yourself. So I promise that I will try not to have lectures this long. But can take a break in between. Anyway, so this was your last lecture of the week. So it's time now to finish your weekly assignment, work on your practice assignment in your lab. Feel free to reach out to me with any questions.